When an API request is initiated, it arrives at your AWS environment's perimeter as a raw data packet attempting to access a secured resource. Simply drafting valid JSON policies does not guarantee that the request will be handled correctly. Syntax alone cannot secure cloud infrastructure. Behind every API endpoint sits a strict deterministic evaluation algorithm. AWS compiles every overlapping rule, constraint, and variable attached to the caller, and calculates an absolute decision to allow or block the action. To understand how access is actually granted, we have to look at the different policy management styles, trace the logic loop of the evaluation engine, map out the unique union between S3 bucket policies and IAM identities, scale paths using dynamic variables, and enforce boundaries using the IAM.passRole constraint. Relying on trial and error to grant permissions leaves data exposed. Mastering this deterministic computation engine is the required baseline for securing enterprise architecture. Building clean access structures starts by selecting the correct policy format. AWS divides access management into 3 distinct policy types. The first type is AWS managed policies. These are created, maintained, and automatically updated by AWS to represent common job functions, like a database administrator or a network engineer. Because they are designed for broad utility across thousands of distinct customer environments, they rarely align with the strict principle of least privilege. They grant wide permissions and should be deployed with caution in production environments. The second type is inline policies. An inline policy maintains a strict one-to-one relationship with a single IAM user, group, or role, and the JSON is embedded directly inside that principle. This creates an immediate governance risk. Deleting a user pertinently deletes the embedded access rules along with them. Inline policies cannot be attached to other identities, and they lack version control, making them difficult to audit. The third and most robust option is customer-managed policies. These are custom JSON documents that you create and manage centrally in your account. They exist independently of any single user. You can attach one customer-managed policy to multiple groups and roles simultaneously. They also support native version control, retaining up to 5 active versions, so engineers can quickly roll back if an edit introduces a security regression. Because of this centralized change management and reusability, customer-managed policies are the definitive architectural gold standard for enterprise environments. Regardless of the policy type you select, when an API request is made, it is processed by the AWS Policy Evaluation Engine. The engine operates on 3 absolute mathematical rules. This is a logic circuit mapping the evaluation sequence. Rule number 1 dictates that the foundational state of all AWS environments is default deny. All incoming requests start entirely blocked. To evaluate the request, the engine compiles every applicable policy attached to the requesting principal, including identity policies, resource-based policies, and session boundaries. Rule number 2 requires the engine to scan this compiled block specifically for an explicit deny. An explicit deny is absolute. If the engine finds a single explicit deny that matches the requested action and resource, the evaluation ends instantly. The transaction is rejected and no further rules are checked. An explicit deny overrides any allow. Rule number 3. If no explicit deny is found, the engine scans the policies for an explicit allow. If a valid allow is located, the request is approved and the API call executes. If the engine reaches the end of the compiled policies without finding a single explicit allow, the process reverts to its baseline state. The request remains blocked by the default deny. This closed-loop sequence ensures that no action can execute on AWS without intentional, documented authorization. This logic applies cleanly to a single IAM user, but the environment becomes complex when policies intersect. Identity-based policies apply to users and roles, while resource-based policies attach directly to infrastructure, like an Amazon S3 bucket. When accessing an S3 bucket, the engine evaluates the logical union of both policy types. Access is granted if either the identity policy or the resource policy explicitly allows the action, provided neither document contains an explicit deny. Here is a 4-quadrant grid showing an EC2 instance role attempting to access a specific bucket named myBucket. We can trace the 4 core outcomes of this logic union. In scenario 1, the instance role has an identity policy granting S3 read access. The bucket has no policy attached. The request is allowed based entirely on the identity's permissions. In scenario 2, the role still has its read-allow, but we attach a new policy directly to the S3 bucket that explicitly denies access to that specific EC2 role. The request is blocked. The explicit deny residing in the resource policy immediately overrides the allow granted by the identity policy. Scenario 3 reverses the permissions. The EC2 identity policy grants 0 S3 access, rendering it silent. However, the S3 bucket policy explicitly allows read and write actions for that EC2 role. The transaction is allowed. Even without identity-based permissions, the cross-policy allow from the resource is valid because there is no competing deny to override it. In scenario 4, the identity policy explicitly denies access, while the bucket policy explicitly allows it. The explicit deny in the identity overrides the resource allow, forcing a block. Mapping this intersection accurately is critical. Misunderstanding the logical union between roles and buckets frequently leads to accidental public exposure or administrative lockouts. Managing access becomes even more challenging when partitioning storage at scale. If an enterprise needs private home directories for 1,000 employees, writing 1,000 separate static policies mapped to individual folder names is an unscalable management bottleneck. The architectural solution is to use dynamic policies. Instead of hard-coding folder paths, engineers use policy variables that capture real-time session context at the exact moment the API call is made. The most common variable, highlighted in this JSON block, is AWS username. When a user requests access, AWS dynamically replaces this variable with the identity of the caller. If a user named Sarah executes a request to read her directory, the engine replaces the variable with the string Sarah. This creates a valid match against her specific resource path, and access is granted. If a user named George attempts to access a file located in Sarah's directory, the engine resolves the variable using George's context. The resulting string fails to match Sarah's storage path. With no explicit allow governing the request, the engine drops the action via the default deny rule. By leveraging dynamic variables, engineers can securely partition isolated storage for thousands of identities using a single, easily auditable policy document. Beyond human users, automated AWS services, like EC2 instances executing back-end code or CloudFormation stacks deploying infrastructure, require specific privileges to operate. To acquire these permissions, the automated service must assume an IAM role. Securely assigning a role to a service requires engineers to navigate two distinct permission boundaries. The first boundary is the service trust policy. This is a resource-based policy attached directly to the role, dictating exactly which AWS service principal, such as lambda.amazon.com, is authorized to assume it. This diagram maps a common exploit vector that necessitates the second boundary. A developer with basic EC2 permissions might attempt to launch an instance and attach a highly privileged administrator role to it, intending to log into the server and hijack those permissions. To prevent this, AWS enforces the IAM/pass role API constraint. When the developer issues the command to attach the role, the engine verifies the developer's own identity policy. It checks if the developer is explicitly authorized to pass that exact administrator role to an EC2 resource. Because the developer's policy lacks the pass role permission for the admin tier, the engine blocks the deployment immediately. The IAM/pass role constraint acts as the ultimate failsafe. It ensures that internal users cannot escalate their own privileges by assigning sensitive roles to automated services. Secure access management requires standardizing your infrastructure on version-controlled customer-managed policies and strictly adhering to the absolute power of the explicit deny. This diagram maps the compiled system in motion. Policies form a logical union, pass the evaluation loop, resolve dynamic variables, and enforce strict delegation constraints. You must internalize this algorithm. Infrastructure as code is meaningless if access controls are configured through guesswork. In the third and final part of this series, we will examine the Security Token Service, Microsoft Active Directory integration, Cognito identity pools for external web identities, and row-level DynamoDB security. You now have the blueprint to evaluate cloud permissions mechanically.